The other ways to access ZDA storage is as ZDA tiles. We'll look into details of how the tiles are formed from the ZDA storage in the further slides. All the while we considered 128-bit implementation, and in 128-bit implementation we saw that the size of the ZDA is 16 by 16 bytes and the element size being 8-bit, and the number of tiles when you have a 8-bit element access is just 1. So we completely consider the ZDA storage as 1 tile when we access for 8-bit element size. However, for different element sizes, like if the element size is 16-bit, for the same 128-bit implementation, the size of the ZDA storage is constant. However, the number of tiles will be 2. How do we form these tiles? Each tile is a square tile, and starting from row 0, all the alternate rows will form 1 tile, and starting from row 1, all the alternate rows will form the next tile, tile 2. Similarly, for 128, for 256, 512, 1024 and 2048, the number of tiles is depicted here. Just for an example, let's look at it from how it looks from visual perspective. Here is a ZDA tile for SVL of 128 bits. The number of rows and columns of 16 by 16. The ZDA storage size is 16 bytes into 16 bytes. And this forms a single tile, and that tile is referred as ZDA 0. The suffix 0 indicates the tile number. So ZDA 0 is a single tile, and the element size access is byte. So this B indicates byte. Now let us extend this and see if the element that I want to access in the ZDA tile is 16-bit. What happens then? As we all have seen in the previous slides, the number of columns will go half of 16. That is, it will become 8. And the number of rows will be 16. Starting from row 0, all the alternate rows form 1 tile. That is tile 0. The one that is depicted in orange color forms ZDA 0 tile when the element size is 16-bit for a 128-bit implementation. So there are 2 tiles here. Both are square tiles. Tile 0 is formed by the alternate rows from starting row 0. There are 8. It's 1, 2, 3, 4, 5, 6, 7 is 8. So these 8 rows constitute 0 tiles, or referred to as ZDA 0. And the tile formed from row 1, all the alternate rows from there onwards, shown in blue, forms tile 1. The H indicates the element size accessed. This is for a 16-bit element size, so half word, H indicates the half word. So we have 2 tiles. Each tile is 8 by 8. This is how the tiles are formed. This is for a 16-bit element size. What happens if I am accessing 32-bit elements? The number of rows will remain constant. However, the number of columns, here we got about 8. The number of columns will further reduce to 4. And the 4 by 4 becomes a tile for 32-bit element size, leading to 4 tiles. When the element size is 32-bit for an implementation of 128 bits, the row 0, row 1, row 2, row 3, row 4, all the orange ones form tile 0. All the rows that is being depicted in the orange color here forms row 0. The line here represents that this is going to be my one element, and each element is how many bits? 32 bits. And the square shown here is for 8-bit element. 8 into 4, that is 32-bit. So there are 4 columns. Because we are accessing 32-bit element size, the number of rows remains same. However, the tiles are 4. The 0 tile is constituted by the rows depicted in the orange color. Similarly, the rows depicted in the blue color forms tile 1, that is accessed as ZA1, and the yellow ones form the tile 2 and the gray ones form the tile 3. Now each tile can be used independently to store a data matrix. Then using just a tile 0 for access in the instructions enables us to perform data computation on a matrix of data much easily, thereby reducing the burden on the program and the bandwidth. That's what makes effective usage of SME for matrix computation. And in addition, there are SVE2 instructions that can directly compute the data between any of these two matrices and store the outer product in one of them. Also extend the outer product if need be to another type. Okay, let's go on. Similarly, if we are accessing 64-bit elements, then we'll have only 2 columns and the number of tiles will go to 8, and each tile will have only 2 rows and 2 columns. A tile is always a subarray of the ZA array, and depending upon the element size, the number of rows and columns in the tile will be changing, and the number of tiles that we derive from ZA storage depends upon the element size that we are accessing. Based on that, it will change, and the number of implemented SVL bits. Again, this is an example extended to 128-bit element size, wherein we'll be using the suffix q, indicating that it is a 128-bit element size, and we'll have 16 tiles. Each tile will have just 1 row and 1 column. That's about the tile, how the tiles are formed. Now, within a tile, we can access a vertical vector array or horizontal vector array. So, complete vertical vector array of data that can be accessed within a tile is referred as a vertical tile slice, and the horizontal ones are referred to as horizontal tile slice. Let's look at it in greater detail. Here is an example of accessing the 16-bit elements, and it is a horizontal access. So the H here suffix to ZA0 tile number. ZA0 represents the 0 tile. The H here is highlighted. Suffix with ZA0 indicates that it is a horizontal tile access. H0, this H says that you are accessing a element that is 16-bit wide. For a 16-bit element size, ZA0H, and this 0 will access 0th slice of that particular tile. We have a ZA0 tile. Inside the ZA0 tile, to access the 0 tile, you'll use 0. To access the slice 0. To access slice 4, you will use this number, suffix 4. And this H represents the horizontal slice. Similarly, if you want to access the vertical slice, this will become, you suffix V to the ZA0 tile name. You are representing that you are accessing a vertical array of data, and where it's what is the element size? That is a 16-bit element. Which is the tile? It is a ZA0 tile. Similarly, for a ZA2 tile, if you want to access a vertical slice, you indicate V, and which is the slice number, that is suffixed to .s, and this S represents that you are accessing a 32-bit element. Right? So as tile slice, we can access a one-dimensional set of continuous data in the ZA tile, which is part of the ZA storage.